Hello, I am Shraddha Banode and you are watching We Learn by Sharun. In this series, we are learning synchronous machines, particularly alternator. And in today's session, we are going to see pitch factor, distribution factor, and EMF equation in detail. Before understanding this pitch factor, distribution factor, and EMF equation, let's revise few of the winding terminologies which we must have seen before, but it is important to understand these terms to understand the later part. I have already explained all these terms in detail in my previous video. I'll share the link in the description box. Okay. Now in this, we are taking an example. This example we have seen before. We are going to take the same example that we are having 24 slots stator and four poles are there. So number of slots per pole, which is pole pitch, is given by 24 by 4, which is coming out to be 6 slots. So we have 6 slots between two poles. So the coil span, now what we are doing is, instead of having full pitch, if we have full pitch, it will be from 1 to 7. Instead of full pitch, we are having a short pitch, which is shorted by 1 slot. So the coil span became 5 by 6 of the pole pitch, while the shorted by 1 by 6 of pole pitch. And in angle, if we talk, it is 180 by 6, which is 30 degree, which is nothing but beta by what the angle is shorted. Okay. So what is pitch factor? Pitch factor is nothing but ratio of vector sum for the short pitch coil to the arithmetic sum if the coil is full pitch. So let's try to derivate this. Let's try to first of all have the arithmetic sum. So if we have EMF induced in one conductor and EMF induced in another conductor of full pitch coil, they will be in phase, and when they will be in phase, the total EMF induced in that turn will be twice ES. The total EMF induced in that turn will be twice ES. Okay. But what about vector sum? When we have the vector sum, when we have the phasor sum, how much will be the value? And before understanding that, first of all, let's try to understand that by how much angle the coil is shorted, okay, and how it is represented. So if you carefully watch this, this is the angle between two slots, and if it is shorted by one slot, then it will be slot angle beta, but the angle by which it is shorted is represented as alpha. So what is the difference between alpha and beta? Let me explain you. Beta is the angle between two adjacent slots always. Alpha is the angle by which it is shorted. Now it can be shorted by one angle, it can be shorted by one slot, it can be shorted by two slots, it can be shorted by three slots, and so on. So depending upon on how many angles it is shorted, alpha is decided. So here, when it is shorted by one slot, alpha is same as beta, no doubt. But when it is shorted by two slots, like in this example, when it is shorted by two slots, so what you are having here, you are not having alpha is equals to beta, but you are having alpha is equals to twice beta because it is two slots, right? So alpha is equals to twice beta here. Similarly here, if you consider the third case, if the coil is shorted by three slots, then alpha will be equals to thrice beta. So what is beta? Beta is angle between two slots always. What is alpha? Alpha is the angle by which it is shorted. It can be one slot, it can be two slot, it can be any number of slots as per the data given. Okay. So ultimately what we will conclude, that alpha is the short pitch angle. That is angle by which the coil is shorted. It can be 1 or 2 or anything. So if you understood this, then we will try to understand this part. So if EMF induced is ES, okay, and this is the EMF induced in another conductor of the short pitch coil. Now why it is going out of phase? It will be going out of phase because it is shorted by angle alpha. Alpha is the angle by which it is shorted. So exactly by that angle, the EMF induced in another conductor will go out of phase, and total EMF we will get is ER. So what is ER? ER is the phasor sum. And what was the arithmetic sum? It was twice ES. Let's consider the same phasor here. This is ES, EMF induced in one conductor of this coil. This is ES, EMF induced in another conductor of the coil, and the angle in between them is alpha, where alpha is the angle by which the coil is shorted, and the phasor sum of this is ER. So ultimately pitch factor is nothing but phasor sum to the vector sum to the arithmetic sum. So phasor sum is nothing but ER here, the resultant of this two, and that is what we are going to find out. To get the value of ER, or to get the expression for ER, let's draw one line here. Let's draw one line here, which will be perpendicular bisector on this ER. Okay. Now let's try to understand the angle, because we need the angle here. So if this is alpha, then can I say this is 180 minus alpha? Yes or no? Yeah, I can say this is 180 minus alpha. So if this is 180 minus alpha, and so can I say this is 90 minus alpha by 2? Yes. This is 90 minus alpha by 2. So this is 90 minus alpha by 2. This is 90. By triangle law, by theorem of triangle, we will get that this angle is nothing but alpha by 2. Right? This angle will be alpha by 2. Now what we will do is we will consider this particular triangle. You can see this triangle. Yes, this triangle we will consider. And what we want ultimately, we want this particular value. We want this value, because in this triangle, if we will get this side of the triangle, ER will be exactly double of this side of the triangle, right? So let's apply the trigonometric expression here. If this is alpha by 2 and this is right angle triangle, this is hypotenuse ES. So I can say this is nothing but ES cos alpha by 2, right? This is ES cos alpha by 2. If this is ES cos alpha by 2, I can say ER is nothing but twice ES cos alpha by 2, because that is twice the value of ES cos alpha by 2, right? So hence we got the expression for ER. So we can say that phasor sum of the short pitch coil is twice ES cos alpha by 2, where ES is the EMF induced in one conductor. Okay. Now let's take the ratio for pitch factor. Pitch factor is given by vector sum to the arithmetic sum. Vector sum we just got as twice ES cos alpha by 2. And what is arithmetic sum? Arithmetic sum is nothing but just addition of 2 EMF, that is twice ES. Twice ES gets cancelled, and we get ultimately pitch factor is equals to cos of alpha by 2. Very, very important derivation, very, very important formula to remember, that Kp is nothing but given by cos alpha by 2. Right. So if we understood this, let's try to understand what is distribution factor. Now, if the winding is not concentrated but distributed among the different slots, as we have told you what is distributed winding, then the EMF induced in each turn will be displaced by one slot angle, क्योंकि एक एक slot angle से वो change होता जाता है, एक एक slot angle से आगे बढ़ता जाता है. So that will be referred to one slot angle. Okay. Now each phase consists of conductors which are distributed in some slots. Now what are the number of slots? In how many slots it will be distributed? That we will see. So the EMF induced in those conductors are not in phase. It is always displaced by some angle, and it will be displaced by some angle means slot angle. And what is slot angle? Slot angle is nothing but beta. So it will be displaced by beta. Now to understand in how many slots it will be distributed, let's take an example. Let's say that there is a 36 slots machine. There is a 36 slots machine in which 36 conductors are there and 4 poles are there. So number of slots per pole will be 9, 36 by 4. But number of slots per pole per phase, which is equals to 3 here, is nothing but M. What is it? It is M. N is number of slots per pole. Number of slots per pole here is 36 by 4, that is 9. But M is number of slots per pole per phase. Now it is 36 by 4 by 3. But you cannot do like 36 by 4 by 3. So 4 by 3 is you take first and then 36 by no. It is number of slots per pole. You will calculate first and then per phase. So it will be 9 divided by 3. I'll just take it here. It will be 9 divided by 3, and you will get ultimately the value of m is equals to 3. Clear? Now what is m? That I'll tell you what is m. M is the slots in where the winding is distributed. So when we say in how many slots it is distributed, in m number of slots it will be distributed. Okay? So let's try to understand this better. Distribution factor. Yeah. Now each phase consists of 3 slots for this particular example. Generally we can say that each phase consists of m number of slots. In this particular example, m is equals to 3, so 3 number of slots. So angular displacement between any two adjacent slot is given by beta, and beta is given by 180 by number of slots per pole. That is 180 by n, that is 180 by 9 for this example, and that comes out to be 20 degree. So beta is 20 degree. So if the 3 coils are bunched in one slot, the EMF induced will be arithmetic sum. If it is a concentrated winding, 3 coils are bunched in the same slot, it is nothing but concentrated winding. So EMF induced in those windings together will be arithmetic sum of EMF induced in one conductor. So if 3 coils are there, the EMF induced in those 3 conductors will be 3 ES, where ES is the EMF induced in one conductor. So simply it will be arithmetic sum. But that is not the case in distributed winding. Practically in distributed winding, vector sum has to be calculated. We need phasor sum, just like we just as have seen in KP pitch factor. We will see similar type of arrangement here. So what is distribution factor? Distribution factor is nothing but the ratio of vector sum to the arithmetic sum. Vector sum is the sum of the EMF when it is placed in distributed type. Arithmetic sum is the sum of the EMF when it is placed in the concentrated type of winding. Concentrated winding. Now what is concentrated winding? As I told you, these terms have been explained before in my previous video. If you want clear understanding about the difference between concentrated winding and distribution winding, please go and watch my previous video. The link will be in the description box. Okay, so it is KD. KD is equals to EMF induced in distributed winding to the EMF induced in the concentrated type of winding, right? Okay, so to understand this better, let's try to take first of all arithmetic sum. ES is the EMF induced in one coil side. ES is the EMF induced in another coil side placed in the same slot, concentrated type. So the total EMF induced will in the 3 conductors which are kept in the same slot will be equals to thrice ES. That is the arithmetic sum. So let's try to get the vector sum as well. Then only we will understand this better, right? So to understand this vector sum better, ES is the EMF induced in one slot, one conductor of one slot. Then another ES will be EMF induced in another conductor of second slot, and this ES will be in another EMF induced in another conductor of third slot. So 3 conductors displaced by angle beta, and hence the phasor angle by which it is displaced is also angle beta. So you can say this ES is displaced by beta angle, again this ES is displaced by beta angle. What is the ultimate aim? To get the EMF induced in distributed winding, that is to get the vector sum. So I'll draw the vector here, and this ER is nothing but going to give us vector sum. So what we are going to do, again we are going to take the ratio for KD, that is vector sum, which is ER upon arithmetic sum, which is this thrice ES. Clear? So to understand this vector sum better, again have the phasor distribution here. This is the ES which is induced in one of the conductor in first slot. This is EMF induced in another conductor which is placed in second slot. Then this is EMF induced in third conductor, right? Which is again displaced by angle beta. This is just as I told you in last slide, right? So if this is 3 EMF induced in 3 conductors of the 3 slots and displaced by beta degree, so the total EMF which is induced, that is phasor sum, is given by ER in the combination of those distributed winding, right? Now to understand this better, what I'll do is, let's assume that this vectors ES, ES, ES are nothing but the arcs of a circle, and accordingly I'll draw this construction line from each point of this vector so that it is meeting at the center of the circle. Now if suppose this is three phasors, like if it is more than three phasors, for example four phasor, five phasor, six phasor, so it will be go on this like this it will go on be out of phase. It will always be out of phase by angle beta. So like this it will form a circle type of structure, and if we take the center of that particular circle, this is the center of that particular circle, and I have just drawn the construction line from each vector of ES, right? So then I will also draw a perpendicular bisector from this center point on ES, which will be perpendicular to this ES. Similarly, I will draw one more perpendicular bisector from the center of the circle to this ER. Okay, both are forming 90° with the ER. Now let's try to get the value of beta. So if we understand that this is nothing but beta angle by which it is displaced, and if we'll try to understand, so we will come to know that this is the same angle which center is forming with ES, right? If this is center and this is the equilateral triangle which has been formed here, uh, right? Sorry, isosceles triangle which has been formed here. So for this particular isosceles triangle, these two sides are same and the angle between them is nothing but beta. So if this vector is forming angle beta at center, similarly this vector will also form angle beta at center, and this vector will also form angle beta at center. Combinedly we can say, as the number of vectors will be there, we will get multiple angles. So m type what is this? This is m is the slots per pole per phase, which is 3 here. So I can commonly say the total angle it is forming is m beta. अभी 3 है तो 3 बीटा, अगर 4 है तो 4 बीटा, 5 है तो 5 बीटा. So like this m beta will be there. Okay, now if this is m beta and this is said to be radius of the circle, that is r, okay, and this is forming 90° with this two, this is perpendicular bisector, I'm considering this particular triangle now. Now if I consider this right angle triangle where this is angle beta, okay, let me use the pen here. Yeah, if this is angle beta, this complete is angle beta, that is just we have seen. So which is this angle? This is obviously beta by 2 because I have drawn the perpendicular bisector here. So this is nothing but beta by 2. Now this is beta by 2, this is 90° and this is right angle triangle. This is R. Can I get the value of this? If I get the value of this portion, half of ES, this will be ES, full ES we will get, right? So in this right angle triangle, if this is beta by 2 and this is hypotenuse R, I can say this side of the triangle is R sine beta by 2, right? And if this is R sine beta by 2, ES is exactly double of it, which is twice R sine beta by 2, right? If this is twice R sine beta by 2, we got the value of ES. That is 1 ES is equals to twice R sine beta by 2. If it is 3 ES as arithmetic sum, it is 3 times twice R sine beta by 2. So in general, if it is M times ES, it is M times twice R sine beta by 2. Just remember this. Let's go to phasor sum. Let's try to get the expression for ER as well. So to get ER, I'll consider this right angle triangle. Okay. Let's consider this right angle triangle, right? Now in this right angle triangle, if this is M beta and this is perpendicular bisector, can I say this is M beta by 2? I'll just take the pen again here to highlight this angle. This is, can I say this is m beta by 2? Yes, this is m beta by 2. This is right angle and this is right angle triangle. So, and this is R. What is this? This is nothing but R. So, this part of the triangle, which is side of this particular triangle, it will be said to be half of ER. And half of ER will be given by R sine m beta by 2. Right? This is R sine m beta by 2. So if R sine m beta by 2 is this side of the triangle, which is half of ER, we can say ER is exactly twice of it, which is twice R sine m beta by 2. So ER here is given by twice R sine m beta by 2. KD, that is distribution factor, is given by EMF induced with distributed winding to EMF induced to the concentrated winding, right? So with distributed winding, we just got it as twice R sine m beta by 2. And EMF induced in concentrated winding. So ES was twice R sine beta by 2. M times ES, so it is M times twice R sine beta by 2. Twice R will get cancelled here, and ultimately we will get KD is equals to sine m beta by 2 upon m sine beta by 2. Very, very important expression you need to remember. If you have distributed winding, you need to use this equation to get the value of KD. KP is given by cos alpha by 2, where alpha is the angle by which the coil is shorted. KD is given by sine m beta by 2 upon m sine beta by 2, where m is slots per pole per phase and beta is the angle between two adjacent slots. Right. Now after this, let's consider EMF equation to get the how much EMF is induced in the conductors. Now we know that EMF basically is given by Faraday's law of electromagnetic induction, which says average EMF induced in the conductor is is proportional to rate of change of flux. So when we say rate of change of flux, it is nothing but change in flux with respect to time, right? Now change in flux means how much flux the conductor is facing in one revolution. So there are number of poles. So each pole is giving 5 Weber flux. So if P is the number of poles and flux produced per pole is 5 Weber, so the total flux any conductor will be facing is 5 times P times 5, like 5 into P. It will be 5 into P. Okay. Now 5P is the change in the flux which is taking place in how much time? In one revolution. So how much time is taken for one revolution? So for that, speed is given by n revolution per minute. But if we convert it into a second, it is n by 60 revolutions per second. Exactly reciprocal of that will be time. So time will be 60 by n seconds. Dt is the time which is taken for n revolution, that is 60 by n seconds. Right? That is for one revolution we can say here. Right? Now average EMF induced is given by d phi by dt. D phi is 5p, dt is 60 by n, and hence we can write it as taking n in the numerator 5p n by 60. So average EMF induced per conductor is 5p n by 60. Now n is the speed by which the mechanical energy is given. So let's substitute the value of n, which is 120 F by P, and we will get average EMF induced as 5P by 60 into 120 F by P, that is equals to twice F phi. It is twice F phi, right? So now this was the EMF induced in one conductor per conductor. If there are Z number of conductors per phase, so accordingly EMF we need to consider number of conductors. So average EMF induced per phase is equals to twice FYZ, where Z is the total number of conductors. Now we can talk in terms of total number of conductors, that is Z, or we can talk in terms of turns. Now what is the relationship between conductors and turns? We know two conductors make one turn. Two conductors make one turn. So when two conductors make one turn, 10 conductors make 5 turn, 20 conductors make 10 turn. So it's simple relation that turn is equals to Z by 2, or Z is equals to twice T. So I'll just replace Z in above equation with twice T, and I can get average EMF induced per turn per phase as twice F phi into 2T, that is 4F phi T. 4F phi T is the average EMF induced per phase. 4F phi T is the average EMF induced per phase. Okay. Now that is the average EMF induced. All the standard electrical quantities we consider in RMS value. So for that we need the relation between RMS and average. And what is the ratio of RMS to the average? Yes, it is form factor, which is given by 1.11. So let's try to get RMS value. RMS value to the average value is 1.11, which is form factor. And we will just multiply form factor with the average value to get the RMS value of EMF induced. So this will give us 4.44 F phi t volts. Now 4.44 F phi t volt is the EMF induced in a full pitch concentrated type of winding. But we know practically the windings are short pitch as well as distributed type. So then what we will consider? We will consider pitch factor and distribution factor just as we've seen earlier. So considering these factors, the EMF will be reduced by some ratio. So these factors are nothing but Kp and Kd. This reduces the EMF induced. And finally, the total EMF induced, the RMS value of EMF induced will be given by Kp Kd 4.44 F phi t, or we can say EMF induced per phase. Just we can say EMF induced per phase is equals to 4.44 F phi t kpkd or 4.44 kpkd F phi t volts. Okay, this is the equation you are going to use to solve numericals and to get the EMF equation for alternator for various conditions. Okay, I hope this thing is clear to you along with Kp, Kd and how to get the EMF equation of the alternator. If you have any confusion, you can write down in the comment box so that I can clear your doubts. If you understood pitch factor, distribution factor and EMF equation and how to find out EMF equation of the alternator, please like my video. And if you want me to come up with more such videos on electrical machines, on synchronous machines, subscribe to my channel so that you can watch my upcoming videos on electrical machines. Thank you and happy learning.